Welcome everyone to this third of our webinars in a whole series throughout the month of May, presented to you by the International CCU Assessment Harmonization Team. We're excited to share with you today the work that two of our sub-teams have spent the last couple of months on, with particular emphasis on how do we actually think about and go about assessing the environmental and economic opportunities of technologies that are just emerging. In other words, at low technology readiness levels. So today you hear about those efforts and how we go across the technology readiness scale. And again, as a reminder, this is one of a number of webinars that are all tied together. So welcome back to those of you who have joined us for the previous webinars, and welcome to those of you who are here for the first time. Today, you are hearing in two parts. First, about how to identify and deal with technology readiness levels in general. The team is led by Tim Langhorst, includes Sheikh Moni, Arno Zimmermann, Shaidle, and Ian Rowe. And with that, I want to give the floor to Tim and his team to share with us what they have worked on. In the meantime, as they get ready to share their slides, I invite all of the participants who inadvertently have logged on as Christiane Kadapong to change your name if you would like to be identified by your real name and not the placeholder in the Zoom link. Thank you, everyone, and I hope you have a productive morning of information sharing, but also feedback from the audience. Tim.
Yeah, thank you for your introduction. While Arno is starting his screen sharing, the presentation will be held by Arno Zimmermann and Sheikh Moni, which are from TU Berlin, respective the NETL, and they will present the results that we came up with and the discussions we had in our technology readiness team. Okay, so Arno, are you ready?
Yeah, thanks Tim and Volker for the kind introduction. So let's get started with the TRL webinar. Thank you for joining. And as Tim said, Moni and I will present that. I have recently transferred from TU Berlin to a newly founded consulting company, Netzero.Partners. Hold on. Okay. So first, we would like to get to know the audience a little bit better, and then second, we will talk about the TRLs in more detail, followed by a further, more detailed discussion about challenges for TEA and LCA. The team members were already mentioned, but I would like to thank each and every one of you who contributed, and also I'm looking forward to the discussion during this webinar, because we have a Q&A session just after these slides here. So Tim, would you mind starting the survey? We have two polls for you, two questions to get to know you. The first one is on your background. So we will allow 2 minutes for you to share your background, which will allow us to better kind of cater our messages to the audience. As you know, we are partly government, partly academia, and transferring to industry. But we usually like to have a broader outreach to various stakeholders. Okay, I think we can go close this poll. I think I share it like this. Okay, great. So you can see that we have participants from all different groups. The majority is from industry, but we also have government and academia and one investor, but not everybody participated. So let's assume that we have all groups presented here today. Tim, would you like to share the next poll, please? Okay, so the second question is, how familiar are you with the TRL concept? So that's important for us to know to cater this presentation to you. So either you have used it frequently, you've used TRL a few times, you used it once, you have heard of TRL, but you're not really sure what it is, or it's completely new to you. And no worries if it's new to you or if you've just heard of it, this is a good presentation. But also if you've used it frequently or a few times, I think we should be able to share some interesting insights with you. Okay, I'm going to close the poll. Last opportunity. Okay, so you can see that we have also, again, a large spread. We have a few who have heard of TRL or it's new, and we have a couple of experts here in the group that are frequent users or have used it a few times already. Okay, so thank you for your feedback here. I think I'll close this poll. Let's continue to the next slide. So first, for everybody who's new to the TRL concept, but also for some experts, we'll have some interesting insights here. First, we'll present TRL in general and then dive down into more details, challenges for TE and LCA. And surprise, we have another audience interaction prepared. So the challenge that we have here today is we would like you to judge the TRL for us. So we have a CO2 carbonation process example here today. And what I can give you is that this process reacts minerals with additives in one step. Now you tell me what TRL do you think this is? And you can choose between TRL 1, 2, 3, 4, 5, 6, 7, 8, and 9. Or you can also select can't say or not sure. And now I'm really curious because my colleagues, we have this constant discussion about what TRL a certain technology is. And it's interesting to see a larger group decide or to get the picture of a larger group here. Okay, so most of you thought, so we have a large spread, first of all, between most of the TRLs. The majority or the larger portion of the audience said it was TRL 9. It's hard to say. I think from this little information, we can't really say that. And let me take the next couple of minutes to tell you why this is and how you can make sure that your judgment or your criteria, the way you choose TRL is more cohesive or more precise. TRL. So TRL is actually part of a larger idea, a larger process, which is called Technology Maturity Assessment. And that was thought up by NASA and the US Department of Energy. And it basically consists of 3 steps. The first is having a technology system and then breaking it down into its critical technology elements. And you can then, this allows you to focus the assessment on the individual elements. The second is then to categorize each of the elements into a technology readiness level, TRL. And then thirdly, develop a maturation plan on the critical elements, especially in how to bring them to a TRL of your choice. So really focusing the R&D efforts onto the critical elements. Now, I'll took the freedom here to copy the TRL scheme of DOE, especially National Energy Technology Laboratory of our esteemed colleague Tim Scone, who presented yesterday, and his team. And basically, we see technology readiness level TRL in 9 levels. So it stretches from 1 to 9. And now let me go through each of these levels. So the first level is just really an idea, a rough concept, a vision, or a strategy paper. For example, we say we would like to mineralize CO2 into some cementitious material, for example. We could use it as a construction material. And then you kind of outline the advantages and disadvantages, the regional challenges, and whether or not it would fit to your organization. Then, if you completed TRL 1, then if you have completed TRL 2, you have a technology concept formulated. You have a list of solutions, and you already kind of know how the future R&D should look like. So, for example, you have written down a couple of equations on how the mineralization could work. For example, you use silicates, you use carbonates, you use others, and you can already kind of, you've looked through literature in the academic or industrial literature, and you've talked to a few experts, giving you a couple of pathways on that you could explore. Now, if you have completed TRL3, you have checked these different pathways in the laboratory. You've really looked at the reactions, and you have a proof of concept. Then at TRL4, you have you have all the experiments kind of documented, and you have more details on the kinetics additionally, sorry. But in addition to that, you also have a rough process concept formulated, so you know kind of what reaction steps should follow each other. And this is all a laboratory environment. And then you go over to a relevant environment where you look at, you clarify, or you increase the data quality further that you have, and you really look at the parameter and property data. You have a more precise process design, a more detailed process design available. And then at TRL6, you have a working pilot plant available. And in terms of mineral carbonation, that could mean a few hundred tons per year, or a few dozen to a few hundred tons per year capacity, for example. Then at TRL7, we're looking into a pilot type of environment, and we really have a pilot plant or a working demo plant, a sample production, which means in terms of mineral carbonation, we're looking at maybe a few hundred to a few thousand tons per year, or even more in terms of system. And then TRL8 is setting up as a kind of a pre-step to the commercial system. So it's the final engineering and all the different certifications that are required, and then also the construction. And then TRL9 is full operations of that system, and it's working in the commercial environment. So the green part here is the commercial environment. Now, this is basically TRL, an overview of what the concept is for the individual elements. Now, let's get into more detail, and maybe interesting for the experts here in the audience, key questions of maturity assessment. A little bit more philosophical maybe, but it's kind of drilling into the issues that we have with TRL. So we've seen that there are various TRL concepts actually. For example, the European Commission has one for the Horizon 2020 program, which is just like one page, and it has been mentioned that the little specification that is available on TRL in this case actually raises more questions than it helps to solve answers or give answers. So you might ask yourself, where's the beginning and the end of such a TRL scale? Well, the beginning, I think, is from wherever basic research stops and wherever we start into applied research. So we don't look into the physical effects or the actual mass properties or so, but what we want to do is we want to apply that basic research. So I think TRL1 starts with the application of research. And the end of the scale, and I think I've mentioned that just in the last slide, is where we actually are in the commercial space. Our readiness levels, phases or milestones. This is also, it's been handled in both ways in current literature, and you can do it as always the way it fits to your organization or to your needs. But I think in general, it's easier to categorize technology elements into TRL if it is a milestone. So you can assume that you have completed certain aspects, and you can actually check a couple of deliverables and then say, we have reached TRL, 1 or TRL5 or TRL7. What kind of scale is TRL? This might be very philosophical, but actually it's kind of important. So it is a so-called ordinal scale. So you can say something is lower or something is higher, but we can't do mathematician operations with it. So we can't say there's an average TRL of this system, for example, or we can't add different TRLs to each other. So just keep that in mind. We can just say it is lower, like one element has a lower maturity or one has a higher maturity than the other. What are requirements to achieve a TRL? And also the next question, how should maturity be measured? This is interesting because there's a lot of discussion about that, and we've seen it a few times in industry projects where, you know, the funding organization thought this technology is a certain TRL, and then the applicant thought it was a different TRL, etc. So it really boils down to what are the requirements and how is it measured? And for that, it makes sense to agree upon or to propose a certain set of criteria and indicators. So first of all, it makes sense to have a certain list of deliverables available for example, for people who apply to a funding program, and not only have them in one aspect, such as the scale, but all in different aspects, such as, you know, what is a tangible work result, where is the work being performed, what kind of outcomes do I have, and what kind of data do I have already, etc. So when I look at it from a broader perspective, I can measure it more holistically, and I can really say, you know, have we already a process concept available, yes or no? And this question is easier to answer than are we TRL4 or TRL5? And then lastly, how does the maturity of system elements in the overall system relate? I think there has been some discussion about that, but overall, it's important to keep in mind that, you know, the system is only as strong as its individual links or its individual elements. So generally, we recommend to assess the TRL of an overall system by the TRL of its, so the lowest TRL of its elements. And if you're curious about these type of questions and want to dive in further, and the chemical industry and TRL and the chemical and energy industry, have a look at this publication here, where we discussed a couple of these questions. Now, I'd like to give you an example here in mineral carbonation. Remember the one from the beginning. So we have already started here to have the overall system broken down into individual elements. So here we have 5 elements. So for the mineral carbonation example, which, by the way, we will also use in the next webinar, which is just following this one, we have the inputs mineral and flue gas, so mineral perhaps from an industrial waste, and the flue gas also from industry, and then we capture the CO2, compress the CO2, we pre-treat the mineral, then we do CO2 carbonation, post-treatment, and then we achieve our cementitious material. Now, if we look on the individual elements, we do have the different steps, and we broke it down further into equipment. In this case, we only used one indicator, so excuse us for this, but for the reason of brevity, I just wanted to explain to you how we judge that in terms of, we basically looked on the equipment and is this critical equipment available commercially, or how far is this currently being developed? Now, with the mineral pre-treatment and with the compression and post-treatment, we actually looking at TRL9. These equipments are commercially available at large scale, and of course we would have to fit them to our current process, but in general we would say these are not the critical technology elements here. However, the CO2 carbonation is probably our most critical one, because our carbonation reactor, we do not have a detailed process model yet available. We just have the first outline. So this is how we judged it into TRL4, and then the CO2 capture plant, in this case, we believed it to be TRL6. This is part of this publication that is currently in preparation, but feel free to ask us or stand by for the publication of this document. Now, and with this, I would like to hand over to my colleague Moni, who will continue on this webinar on the challenges. Let me just hand over the remote to you, Moni.
Thank you, Arno, and good morning and good afternoon to all. So Arno explained the TRL scale and also how to define and what questions to ask to evaluate or identify the technology readiness level. I will focus on the challenges that we can face while performing life cycle assessment or technology techno-economic analysis of emerging technology, and how to relate those with TRL scale. Okay, yeah. So Just before going into the discussing the challenges at first, let's here is an example like how the LCA, the goal and scope of the LCA or TEA can vary based on the maturity level or technology readiness level of an emerging technology. So here is an example of LCA expectation at different TRL level. So in NETL guidance document, I took this from NETL guidance document here and just summarize it. So at all the TRL, when TRL 1 to 4, as Arno mentioned, when we have just lab level research, the LCA expectation, maybe this is screening level LCA. And at this maturity level, the LCA or TA results can allow approximation and assumptions to provide some initial estimate. So to perform a full scale LCA or TA analysis at this level is very difficult. But why it is important, because at earlier stage, it is more flexible to define different process parameters or do some kind of optimization to change the technology. So that's why at this level, performing LC and TA is important, and it can provide some hotspot analysis or some initial estimate to support technology developers. When we have more the technology matured a little bit at 5 or 6, when we have the lab, when we have pilot scale setup, then we can call it a project level LCA, and the knowledge from scale-up demonstration can be included in the LCA or TA modeling. The site-specific conditions or how the scale-up technology market will be there, that can be considered in the technology, and it can provide more details analysis there. When the technology reaches at TRL 7, that we can also call project level LCA, but it will be more details. So it's similar to TRL 5 or 6, but the expectation will be to update the technical performance as more data is available, and also to include some real world performance criteria, how the technology will perform in the real world environment. And that when technology reaches at 8 and 9, that is the project level LCA or full scale LCA or TA studies can be performed. Now you see, based on the technology readiness level, as the goal and scope of the LCA may change, and also the result expectation from the LCA or TA study can also vary, and it can support technology developers or policymakers or investors in different way. So that's why the technology readiness level is very important to consider while performing LCA and TEA. Now, in this work, we mainly focus on the low TRL scale, that is TRL 1 to 5, and what are the methodological challenges to perform TEA and LCA at these low TRL levels here. So there are different challenges, and some of the challenges are similar to the traditional LCA and TEA. However, for emerging technologies at low TRL scale, there is very limited data available, and some of the challenges are very extreme. So we can categorize the different challenges in 5 major categories, and I will go over these 5 major categories a little bit detail in next slides. So the comparability, that is how to compare this emerging technology with existing alternatives, then what are the data limitations, issues there, and also whether we need to consider the scale-up issues and how scale-up issues can hamper the results, and also uncertainty, and then the assessment time. So let's talk about the comparability. So at low maturity, the function of the technology is not always comprehensively defined. And also it can change with increased maturity as more information is available. So just want to clarify, it is not saying that that function, we don't know the function, but sometimes it comes with emerging technology is not always a direct replacement of existing alternatives. It may have unique functions or have other functions. So it creates multifunctionality problems. So the proposed emerging technology may have the multiple functions, and that needed to be considered while comparing with an existing technology or existing alternatives. Emerging technologies, the functionality equivalent is another issue. So how to, while comparing with existing alternatives, how to make sure the functional equivalency that is a challenge while performing LCA or TA of emerging technologies. And also difficulties with direct comparison because of the unclear co-product uses, the disposal strategy, that always a challenge while comparing emerging technologies with the alternatives one. So these are the issues that we need to focus on or consider while performing LCA and TEA at low technology level. Let's talk about the data. Obviously, data limitations is an issue at low TRL because that you only have the initial process description or initial process flow diagram. So, and also sometimes the new emerging technology, it may include the new materials or new catalysts. So to get the inventory data or the process information is very challenging for emerging technologies. And a lot of time the data is confidential. So how to handle these data limitations due to these new materials, new catalysts, or new sources, and also this confidential issue, that's another challenge that we need to focus. And primary data collection may take too long to gather. So while the technology development process is first paced, so sometimes the impact assessment method or for TEA, how to calculate the capital expenditure or the operational cost based on this initial process description is really difficult. So, and data limitations comes with a lot of uncertainty too. So how to fill this data gap and how to getting the quality data is another issue. So while discussing these challenges in different categories, but I want to make sure like it is not totally exclusive. So some of these challenges are overlapping. Suppose the data limitation will create the uncertainty that we'll discuss details in the next slides. So these issues are also related. Now, let's move to the next slide where we'll discuss about the scale of issues. So here you see that at low TRL, we have lab scale information, but while we're comparing with existing technology that is at industrial scale. So how to scale up this lab scale to pilot scale or to pilot scale to ultimately industrial scale and compared with existing alternatives is an issue. Because at lab scale, it is the process is not always integrated together. The equipment used at lab is different from the industrial scale technology, and also sometimes it is not using same process. So the process that is using at industrial scale may be different from lab scale. So using lab scale data to perform LC and TEA and compared with industrial scale alternatives does not always reflect the actual results. So it may mislead the decision making only to lab scale data is used to perform LCA and TEA. So the scale-up issue, like to develop a scale-up framework while performing LC&T at low TRL is another challenge. Uncertainty and uncertainty communication is also very important. We know with traditional LCA, obviously there are uncertainty issue, but for emerging technology, it is also very extreme because we have some of the issue that is known, and there is also unknown uncertainty here. So obviously there is uncertainty associated with the input data and model because the quality of the data is not always good at low TRL, and also there is the data limitations. There is also uncertainty associated with the model. So while performing LC and TEA, how to handle those uncertainties is very important. And another important part is to understand what is the implications of this uncertainty towards TEA and LCA results. We perform sensitivity analysis, we try to rank, but what is the actual implications in the decision making? How the investor will decide based on this decision making, or what would be implication for the policymakers. So that is also important. So communication, like how this uncertainty will be communicated with when presenting the results, that is very important too. So the proper communication of uncertainty to decision maker is another issue, another challenge to perform LC and TE at low TRLs. Okay, yeah. Now the assessment time. So here we also want to talk about obviously getting more details data or gather more primary data is important, and that will help with the with the accuracy of the TE and LC results. But it is also time intensive, and it comes with a cost. So there is a trade-off between the detailed assessment and time intense, and the cost and time needed to gather more data. And also the flexibility to change any process parameter or optimize different process parameters at low technology is more flexible compared to when technology reaches at a higher TRL level. So the assessment time is critical to support technology development. So here, this is also another challenge because we can't perform a very detailed LC or TA at low TRL, but we need to come up with some simplified methodology or shortcut method that may be more effective at this low TRL level. So we can obviously discuss or come up with an ideal methods like, yeah, we need to consider all these impacts, all these factors, everything, but whether it is applicable or whether it is actually applicable at this low TRL level. So that's another issue, how to perform trade-off between these ideal methods and also a method that would be more effective or applicable at this low TRL level. So with that, we identify some of the challenges to perform TE and LC at low TRL level, and this work is also ongoing work, and we want to get feedback from the audience, like what other challenges that you also face, or you can think of when trying to perform TE and LCA at low technology level. And in future, we'll be working on to how to resolve these issues and come up with a consistent framework of methodology. So in this presentation, Arno going into details about how to define technology readiness level and how we can evaluate a TRL of an emerging technology or a study. And I go over some of the challenges that we face while performing LC and TA at low TRL level. So here is also our contact details. If you have any comments or questions, we really appreciate that if you contact us, and we'd love to answer any questions that you have. Thank you. And with that, Arno, if we have the control of the slides.
Thank you, Moni. So I hope everybody had a good time and thought the presentation was insightful. We have 2 questions so far in the Q&A, which I think we can now continue to answer, right? Tim and Moni, if you would like to chip in, just tell me. Maybe I'm going to take the first one because that was about in the example where so minimal combination example. Why did you say you believe that MIA was a TRL 6? What's the engineering background behind that? I think so. We judged it from the available data to us. So we always look at the proposed system as explained by Tim Scone yesterday. What do we have as in terms of data? And for us, we had data for the amine absorption TRL 6 available. So this is why we have judged this as TRL 6. If you have a better data and a better process data available to you, then of course you can have a higher TRL. So this TRL assessment or categorization for your system is very dependent on what data, for example, you have available. It's not that there is one TRL of, holistically valid for the entire world, saying, for example, that methanol from CO2 has reached a TRL X, but there might be an organization that has reached that technology readiness level 9, whereas others might not be there because they don't have that process or that IP available for them. So for us, we judged it as TRL 6. With the next question, Moni, would you like to go with that, or Tim?
Sure, I can go with that. So thank you for the question. What may be the role of process simulation to obtain the data needed when the process is still under development or is poorly known? Yeah, the process simulation tool can be really helpful at low TRL level, but I want to make sure, like you have to enter some inputs in the process simulation software, like sometimes we use Aspen. So if it is based on some primary, like the lab scale data, some the input that you found, and you can run the process simulation based on those data, then it can provide some scaled up data there. So in that way, process simulation data can help to provide, to get some process data, and that we can use for TE and LCA. However, we need to make sure what inputs we are using for process simulation is good. So you have to perform some data quality assessment there. Tim, you want to add anything?
Yep, I already liked your explanation, and I would just add to this question that it could also be looked at vice versa. So what role can LCA and TA play in supporting what's coming out of the process simulation and evaluating what's coming out and finding where we're still inconsistencies or data uncertainties are within this model. Yeah. So the next question. So someone already put the questions to answer. So what's the next one? Okay, here the next one is, I wonder what the risks of low TRL assessments are. How likely is it that a poorly done study or a study with too little data will actually misguide the technology developer and lead to the tech failing when it could have succeeded? Yeah, that's a very interesting question, and this is one key question to the reason why we are going to publish low TRL guidelines in addition to the existing guidelines available from the Global C2 initiative. And yeah, it's quite likely if you do not take care of this. So you really have to go for an iterative approach here. So you have to iteratively communicate to the R&D department when doing TA and LCA to take care of these uncertainties and really report the uncertainties towards these groups and explain where the data should be better and what the sensitivities to the results are. And yeah, this is a key element, the reporting and the interconnection between those groups, the ones who deliver the data, the ones who use the data for assessment, and if it's someone else, the ones who make the final decisions. Hope this answers the question. Do you have anything to add?
I would add something and then take over the next two questions. So exactly, I absolutely agree with you, Tim, and pointing out, you know, never trust the technology assessment. It's very much likely to be wrong, but the point is not about the exact number. It's more or less about how, you know, what are the most important levers? What are the critical elements? What are the critical cost drivers? Where do we have most emissions coming from? And how do these aspects change under a certain set of new scenarios that we're going to look at and which are likely or unlikely in the future? And what we are trying to do is, if you want to improve your assessment or learn more about it, then you can use these guidelines from GCI or NETL, or the new ones about shortcut assessment or low TRL assessment. So we're trying to help you there, but of course, if a technology assessment is fairly done and it comes across that you know, maybe it's not worth doing this technology, there's always some subjectivity in technology assessment, and that needs to be acknowledged for sure. And there was another chat comment that TRL is subjective, and I absolutely agree. However, we are trying to make it less subjective by defining criteria where everybody, you know, agrees, and then we can discuss these individual criteria. Whereas, you know, then we don't discuss is that TRL 5 or 6, but we can say, do we actually have, what type of process do we have available here at this moment? Is this rather conceptual, or do we have a detailed engineering available? And these questions are easier to answer than the very big ones. So I'll mark that as answered. So the next question is the conclusion that the overall technology TRL is equal to the lowest TRL component. Yes, so this is our recommendation, right? So this is also recommended in the GCI guidelines. So if you look on the overall system, you have the individual elements, you categorize the TRL for individual elements, and the lowest TRL, the lowest TRL of the element represents the TRL of the overall system. If you're able to increase that TRL of that element, you are able to increase the TRL of the overall system. So I'll hope that was clear, and move on to the next question, a follow-up question about the MIA capture. SAS Power has a commercial solvent-based capture process. Doesn't this make the process a TRL of 9? Exactly. So if you are able to source that process and you are able to use the data for your assessment from that process, you could judge this to be a TRL 9. And I think there are a couple of capture processes available at larger scale or at commercial scale. But if that data is not available to you, and we have to, you know, use, for example, in our case, we use usually academic data or pilot data, then we can't claim that this is of TRL 9. However, in our case, it doesn't make a difference because our critical element is a TRL 4. So just make sure that if you take something away from the TRL aspect, is that your assessment really depends on the maturity of that technology. So if it is very early, you can't say much. You need to be more aware that there are some downsides, and maybe you need to adapt your methods, and you run into these challenges that Moni described. So, and if you are in this situation, then pay attention to the new GCI guidelines which are coming out, which Tim helped to put together. And with this, I'd like to close the last question. And currently, we have no more questions
So I think we're right on time. I'm not sure if the other group plans to have a short break in between, or if they would like to go directly on with the next presentation. So for Farid, what do you think?
Yeah, good morning. I think probably it's more Christy have to decide. I don't know whether people who plan to participate on the next one to TLC, whether they're not there yet. I think it's originally was planned at 10:30, but that's I will leave it to Volker and Christy to decide.
All right, Tim, thank you for raising that question. First, let me thank Arno and Moni for this presentation and discussion. Of course, the entire team for getting us to this webinar. I think we are only using one sign up for both parts of the webinar, assuming that participants are interested in both parts. We've grouped the topics accordingly. So with that, I would like to invite Tim Scone to introduce part 2.
Thank you, Volker. It's been a great session so far, and I'm looking forward to this next session. And I have the opportunity to introduce part 2, which is the assessing current technology learning curves and their use for emerging CCU technologies. I'd like to introduce Farid Bensebaa, Andrew Rudinger, and Till Strung to talk about their work from their team in moving forward on technology learning curves. Farid, I'll turn the floor over to you.
Thank you, Tim. Good morning, everyone. My name is Farid Bensebaa. I'm a Senior Research Officer at the National Research Council. I am also an adjunct prof at the University of Toronto in the Faculty of Civil Engineering. I am quite honored to coordinate this this webinar today. I'm thankful also to the GCI team who trust me to lead this working group of very, very young, talented scientists. I would say very, very talented young scientists, and not very, very young, but I think it's young scientists. I think now I should be able to share my presentation. Okay. I hope just a thumb up if you see my my screen, my presentation. Okay. The title is there. Let's move to the next slide, which is the outline or the agenda of this presentation. First, I will welcome and present the team member or the working group. We will define the main challenge we want to address. We try to address in the working group. After that, we will provide some literature review. Every time when you try to address a challenge, the first thing you do, go to review what has been done. And from all the different methodologies that have been developed in this area, we choose one. It doesn't mean it's the best one, but it's the one which is going to be, we think it's appropriate given the availability of data mostly. We will provide two case study where we applied the methodology that we have selected, and at the end we'll end up with a Q&A session. And first thing first, I would like to give an opportunity to each team member to introduce themselves.
Okay, the first one. So my name is still Tim Langhorst from RWTH Aachen in Germany. I also have an affiliation to the ETH Zurich in Switzerland. And as many of our team members, I was part of both of these groups, and hand over to Sheikh Moni, who already gave the presentation.
Thank you, Tim, and thank you for it. My name is Sheikh Moni. I work in the NETL LCA group. So I work in carbon utilization and coal beneficiation space. And also my other work focuses on life cycle assessment of emerging technology. Thank you.
Hi, everyone. My name's Andrew Rudinger, and I was a student researcher at the National Research Council Canada, of course, located in Canada. We work on technology learning curves, as you'll find out in this presentation. I'm also affiliated with Cornell University as a PhD candidate there.
Hi, I'm Trl. I'm from the Institute for Advanced Sustainability Studies, which is based in Potsdam, Germany. And I work here as a research associate in the CO2 utilization and society group. And I also do my PhD in the meanwhile at Farid University, mostly on techno-economic assessments.
Unfortunately, Michel van der Roos is not available today because of a personal reason. I think it's, but he was also a key member of this working group. Arno?
Sure. You heard from me before. My name is Arno Zimmermann. I just finished my PhD at TU Berlin and now have moved on to found Netzero.Partners, and I focus on techno-economic assessment of various CCU pathways, including chemistry, polymers, cement, steel, etc. So if you have any questions, feel free to reach out. And yeah, with that, I'd like to hand over to Lynn.
Hello, good morning, good afternoon. My name is Ling Tao. I'm working for National Renewable Energy Laboratory, or shortened for NREL here. I have been focusing on techno-economic analysis, strategic analysis, and other type of supply chain analysis.
Thank you, Ling, and you are also the colleague of this working group. I already introduced myself. Let's move to the next one. The next agenda item is what is really the main challenge we're trying to address in this working group. Before discussing about the main challenge, I want to provide some kind of baseline definitions. The learning curve provides a measure of increased efficiency in the overall process. There are a lot of factors that affect this efficiency, or basically the learning curve, that can include labor efficiency, unit efficiency, optimization of the product design, and the scale. The learning curve basically defines the reduction of a rate of economic and environmental indicators. We'll come back to that point through iterative improvement of the technology during development and deployment. Here, we'll insist on the separation of development and deployment. Development basically is mostly through research, and basically deployment what's called, but through doing it and future a different stage of will come up with the commercialization. What is really the challenge? It's the GCI has developed guidelines in terms of technology for LCATA. One of the guidelines is like how to forecast the performance of emerging technologies when there's a lot of unanswered question, when you don't have even the complete system already deployed. And in here, we will use mostly two indicators: cost, or mostly capital and operation cost, and GHG emissions. Then one other challenge, how basically we can integrate this technology learning curves, methodologies or tools to current TLCA. And as going to be presented in the next slide, in the next item, is basically we found out a lot of approaches have been developed, and we will select one. And just to insist on the on this challenge, it's really it's really how the one way to ask the question. Okay, for example, it's in 5-10 years, current technology which are low TRL, TL less 4 or less, how this TRL are going to behave once they are going to be deployed, if they are deployed. Then the next agenda item, it's about literature review. And Andrew, it's yours.
Wonderful. So thank you for the introduction. So when talking about this technology learning curves, I like to consider this in kind of the very broad space of policy and innovation. And so what you're seeing on your screen here is essentially that. You're seeing this innovation system, its internal and its external factors and inputs. And one way to think of this, you can kind of think of this complementary as what we discussed earlier about technology readiness level, where earlier TRL will fall into maybe this research, development, or demonstration categories, and later ones closer to the market formation and diffusion. Now, in terms of technology learning curves, the most important thing to take away from this innovation process is the technology push section, which occurs at the earlier stages. Click, please. So when you're looking at this technology push, this is for earlier stage TRL, CCU technologies, and often it comes in the form of funding. And how that is actually realized is real cost reductions as you move further in this innovation process, perhaps through capacity increases or things of that nature. So for CCU technologies at a very early stage, this is very important. And a lot of how we kind of encompass this is through learning or technology learning. From a analysis point of view, we might want to figure out how to harness this, maybe model it well so that we can actually make good projections for future and apply that for things like decision-making, policy-making, or research in general. And so how that's encompassed is through learning curves or experience curves. Click, please. And so learning curves or experience curves are what you see here. And it's essentially, like I said, real cost reductions with increasing capacity. Often that's given over time as well. And it's been successfully demonstrated for two well-demonstrated technologies. So batteries, which you see on the bottom left there, and solar photovoltaics, which you see on the right. Why it's has been successfully demonstrated for these is because of the data availability. And that's something that was talked about earlier, that the data is very important in these cases. The issue with CCU, of course, is that we might not necessarily have this great data. And so you have to find a way to be able to use this modeling approach while realizing the limitations of your data. And so this is why this question gets posed, and I put that at that bottom point, is how do we extend this learning curve or experience curve technology to assess these CCU technologies. And so we did quite an extensive literature review, and we arrived at basically a tier-based method. So click, please. And so how this works essentially is that whenever possible, you would use whatever is the most accurate method for calculating the learning rate. Ideally, you would have primary data from maybe some CCU technology that's been demonstrated at a large scale. Unfortunately, because it's at such an early stage, we're probably more likely to fall a little further down this scale. And basically, how we take this approach is that we continue to kind of move down rungs to make up for these holes in this data availability. And so, for example, we might take a learning rate from literature. More likely, as you'll see for the CCU technology, is that we take it based on similar technology and literature. And one example I'll give for that is if you consider CO2 electrolysis, which perhaps hasn't been demonstrated ubiquitously at a large scale. However, something like a hydrogen fuel cell may have been demonstrated and is a little further along in its learning curve or its TRL. And the technology there is quite similar in terms of the electrocatalysis side. And so you might use learning rates demonstrated there and apply it to the CO2 electrocatalysis. And then, of course, you can go further down this rung and use things like general rule of thumb learning rates or other projections. And so you'll see this applied in the case studies that we have coming up. And then lastly, next slide, please. There's a few other key takeaways that is worth mentioning just to consider when you're doing these types of analyses. So first, cost floors are very important, and this could also be applied to greenhouse gas emissions if you're looking at an environmental side. That's important because it helps to not underpredict costs or environmental impact. Second, combined learning rates. So those tend to be common, one-factor learning curve versus two-factor learning curves. The issue with that is that they are typically larger than ones that are disaggregated. Of course, when you disaggregate these learning rates, you run into more issues of data availability. And so we decided to take the approach of a combined learning curve, just acknowledging the fact that it might overpredict. Third, determining cost drivers is very important for informed predictions. Often with this CCU technology, electricity consumption tends to be a very driving factor. And so acknowledging that and making that component as accurate as possible goes a long way in the accuracy of the overall projection you make. And to that point too, cost drivers do tend to shift as you move along your TRL. So for example, at early stages, learning by researching is very important, and you see most cost reductions through that mechanism. Whereas when you go to larger or higher TRL, you run into cases where economies of scale tend to be the driver in driving down costs. Fifth, if data is available, generating experience curves on a component basis rather than a whole system is ideal. There's 2 reasons for that. So the first is that experience curves for CCU technology isn't necessarily readily available because of those data limitations. And so doing this on a component basis and comparing it to similar technologies is actually useful from a pragmatic approach. And then second, it gives you the resolution to be able to actually pinpoint which parts of the system are actually driving down your costs better and which ones are lagging behind. And that allows for more targeted innovation or funding or research. And then finally, sensitivity analysis is very important. And while we don't explicitly show this in our case studies, there's a lot of uncertainty surrounding these choices of learning rates. And so always doing a sensitivity analysis allows you to understand kind of the spread or the range of where these projections could go in the years down the road. And so with that, I'll end it there, and I'll turn it back to Farid for the methodology.
Thank you very much, Andrew. Yes, the next agenda item is the methodology. I'm going to be brief because this methodology will be basically expanded when we're going to discuss the two specific studies. The two common things I want to insist here, it's the right now the one we choose, which is the combined learning rate, which is based on the total plant cost, and the total plant cost of the net plant. Basically, it's will be obtained through the total plant cost of the first of kind, and multiplied by the n and exponent to minus b, and the b basically it's the combined learning rate which will be obtained from the different component. Why we call them the hybrid? Basically, the first of kind will be estimated using more or less conventional cost analysis. We're using a bottom-up approach, and we use then the combining learning rate to estimate the total plant cost of the nth plant. And the next one, I think one of the things we're trying to address also here in this working group, which is, I think I would say it's more like a work in progress. It's how also we can use the similar approach to calculate GHG emissions, and we will use here mostly the material energy and material consumption as a proxy in terms of we're using the calculating GHG emissions. And yeah, I think that's basically unfortunately, one of the things we realized in the literature, there's very few data. Probably this is one of the action items could be suggested following this working group. A lot of data on costing analysis, both CapEx and OpEx, but very few data available regarding the evolution of GHG emissions. Yes, as I mentioned, that's we'll use try to highlight this methodology through two use case studies. The first one is direct aqueous mineralization, and I think Trl is going to be leading the presentation.
Okay, thank you very much. I will present briefly what we did in the mineralization case study. And for this, I want to start a little bit with a small introduction of why we chose this case study. And what you see here is are the CO2 emissions. And we see especially that in the sector industry, we have one industry sticking out, and that's the cement industry. Because the cement industry emits roughly 5% of the global CO2 emission by itself. It's very crucial to find solutions in this sector. And this case study is also being handled in this sector. Next, please. Okay, so if we look at the cement production process, then you see this is usually how it's depicted. So it starts with acquiring the raw materials, which is usually limestone. And then we have a couple of crushing and pre-treatment steps until we reach a very crucial point, that is the step number 6 here, the clinker production. And here we have a calcination reaction where our limestone is calcinated and CO2 is released from this reaction. And these process inherent emissions make up actually 60% of the whole process. And this is why it's very crucial, because if we have strategies where we can reduce, for example, the amount of energy we use for the entire process, we will still stick with these process emissions. And therefore, CO2 utilization technologies and CCU and CCS technologies might be very crucial for the cement industry. And one concept that has been developed in this field is the mineral carbonation. Next slide, please. And this is why we chose this for our first case study. And for that, we looked into what kind of processes are out there. And what is very important here for the cement industry is that in the end, you see on the right-hand side that the product that you produce is a cementitious product. So it could be used as a cement additive, as an aggregate in concrete production, or as a filler. The overall process you just saw also in the TRL presentation, but it works in the way that minerals, in this case, we assume olivines, so magnesium silicates, they are mined and then they have to be grinded to be activated, which is here called the pre-treatment. So mills are used for that. And then it goes into a carbonation reaction, which is quite straightforward. It's in CSTR reactors with under elevated pressure and elevated temperature. And then in the end, there's a post-treatment step to remove the slurry. And for the flue gas, we have, as described before, a CO2 capture plant. So we assume MEA capture here as well, and the CO2 compression. Next slide, please. And so what we first did is we looked at the capital cost of the system and looked at the learnings of the capital cost. So we assumed that we would have 20 plants being built until we reach the nth of the kind status. That can also be transferred then into a percentage of cement plants that will use it. I will show it to you later. And then we have to assume the contingencies. For our first approach that we did, we were looking into if it's possible to just take learning rates from a similar plant and apply these. So what we used here is we found estimates that estimated the coal combustion with CCS and the learning in the future from this, which when you look down into the process units, it had very similar equipment. So we assumed that this is could be our overall learning rate. And then the process to contingencies we selected for the entire process. Next slide, please. And this is the result what we obtained. So we see that from the first of a kind plant to nth of a kind, which is in this case assumed at 20 plants being built, we have a specific capex reduction of approximately 45%. And you can also see that if you have a different question, for example, you want to know how expensive the third plant is, you can also do this with this method, and that is very helpful. Next slide, please. But what you also have heard in the literature review section of this presentation is that it's always better to do these estimations based on each individual component. So that's what we did in the next step. We looked at all of our different units and we selected estimated learning rates depending on the technology readiness of each unit. So we assumed something that is less ready will have higher learning than something that is more ready, has a higher technology readiness level. And then at the same time, this is also suggested in the hybrid method, which we follow, which was published by Ruben. You see this down in the reference list. The process contingencies now are selected for each unit and not for the entire process. So they are also dependent on how far your development for each unit is. Next slide, please. And what we see here now is that we come to a very similar result. We see that the overall, if we do this, if we have a learning rate that we derive in the individual unit level, we, in this case, got a bigger learning rate. So in this case, we see a stronger decrease in the capital costs. But we see that for this particular instance, both might work. But this has to be said, it's very crucial that the learning rates that you apply to your system or these estimations that you find, that they fit to the process and the process units that you use. And next slide, please. At last, then we try to use the environmental learning approach. And this is, as Farid has already mentioned, is a little bit work in progress at the moment because it's very difficult to actually do this. And what we did there, we looked at the greenhouse gas reductions through our proxy, which is the increasing the yield and the additive use, because we found in literature that a main driver for the emissions are actually the yield that you get in the carbonation reaction and how much you can reuse your slurry. So we started with the first of a kind plant, and this is the assumptions that we took from literature that they are taken currently, and then said, okay, we apply these learning until we will reach our floor, which has to be where we have 100% reaction yield and a recycling factor of 100%, because more is not possible. Next slide, please. And then you see with this approach, you can also see the greenhouse gas emission reductions that you would get through the technology learning. And we would see here that at 10 plants, we have a emission reduction of 40 tons CO2 equivalent per ton of mineral. And we would reach our floor already at approximately 20 plants, which was our nth of a kind estimate before. So the difficulty that we have found here in this is especially to find the right learning rate. So we assumed that the learning will be equivalent to the learning that we have on the CapEx. And that is some of the most difficult things we found here. And we are very happy to hear your thoughts, especially also on the environmental learning. And with this, I will give it to Moni to present the other case study that we did. Thank you very much.
Thank you, Till. Yes, Moni and Ling will be co-presenting the next case study, which is around for CO2 to jet fuel conversion. I think it's Ling is going to start with this, right?
Sure, absolutely. The transportation sectors generates a significant share of greenhouse gas emission. And based on the US EPA data, US transportation sector actually generate about 28% of total GHG emission for the country in 2018. And it's the largest contributor primarily coming from, burning fossil fuel for our cars and trucks and airplanes, ships and trains. So this pie chart is illustrate contributions from light duty vehicle or medium heavy duty vehicle, aircraft, ships, and other sources in the transportation sector. So we're thinking reducing transportation-related greenhouse gas emission through decarbonization is the primary problem in chasing or the race against climate change. To contribute meaningful effort on this, we selected a case, basically second case study on conversion strategy using CO2 as the feedstock to produce jet fuel. So next slide, please. This one is actually showing a process concept of using CO2 as the feedstock going into the jet fuel. So you can see that various CO2 sources has been considered. And then we use electrochemical conversion of CO2 to produce CO combined with the renewable hydrogen, and we can make a syngas. And then the syngas will go through the Fischer-Tropsch synthesis to make hydrocarbons. And those hydrocarbons can be fractionated into gasoline, diesel, and jet marine. If you ever study the Fischer-Tropsch synthesis kinetics, and you can actually targeting more to the jet range hydrocarbon by changing the some of those callus severities and loadings. The process actually we put into 3 major sectors, and one is the carbon capture, and one is the electrochemical conversion of CO2 and to syngas, and then the Fischer-Tropsch synthesis, the FTS part. And the uniqueness about this case scenario is in comparison with the previous one, is for each core conversion part, they don't have the same level of technical TRL. And you probably heard the previous webinar on the TRL. I know this number can be a little bit judgmental, but what we, based on all the team consensus, we believe the carbon capture as well as the Fischer-Tropsch synthesis are basically at the commercial scale, so they're high in TRL. However, the electrochemical conversion part is the newly developed area, so we estimate the TRL is in between 2 to 4. And it's still at the lab scale testing and demonstration. So in the next couple of slides, we're going to show some results on the learning rates of this process, similar to case study. I think Moni is going to present that part. So Moni.
Thank you, Ling. Okay, so also Teal already, while describing the first case study, described the methodology in details. So we also use the similar approaches and perform trying to find out the learning rate of the jet fuel production here. So here you can see that there are different factors, and we also make assumptions of here as the 5% as earning rate for system element. And if you see the graph here, and we also make assumption like 18 plants is needed to reach enthalpy kind, and different assumptions related contingency. And here you see that the overall learning rate is 5.88% here, and yeah, they use the CapEx from to 1100 to here after the 10 plants is something near 900. So also as the electrochemical conversion is a very low TRL here, so it is very difficult to make assumption what would be the learning rate as there is data limitations. So next slide, please.
Somehow. Okay. Oh, okay. Sorry, I didn't. Yeah, I think you covered that point, right?
Yes. Okay. So we can get.
Yeah.
Okay, so as Teal mentioned, it is very difficult to apply a learning curve while performing life cycle assessment here because it takes like historic data to develop these learning rates and then apply here. But as Teal mentioned, the methodology we want to relate like from the TA analysis, the gap X learning rate, the similar learning rate can be applied to environmental impacts. So in this case, we mainly focus on greenhouse gas emissions, and also we kind of make assumption rather than calculating the greenhouse gas emission directly, we consider the process yield and also the recycle of different materials. And you see that we also considered like the maximum limit is obviously 100% process yield and 100% recycle. That is the best case there. And we consider different elements and learning curve, the overall learning curve. And when it is applied here from the very first of a kind plan that is around 750 ton of CO2 per ton of jet fuel, it reduced to after 18 plants to something near just over 600. So that is one way to apply learning curve while calculating environmental potential environmental impacts. But as you have heard from other presenters here, it is still developing idea, and it's still challenging how to use this learning curve while evaluating the potential environmental impacts, because it takes data, and as low TRL scale technology, the data is limited. So that's very challenging, and it's one area that need further development. Thank you. Back to you, Farid.
Thank you, Moni. I think we came to the end, and now it's time to have answer some questions that have been already raised. I think I saw there was a couple of questions has been already answered. The next question I'm seeing now, it's, are experiencing curve adequate to predict the evolution of the environmental impact of a given technology, or are there better methods? I can start with this. Maybe anybody from the team can add. Yes, I think it's, as mentioned during the presentation, it is quite challenging to assess the environmental impact, particularly we have the lack of data, also lack of published work. And here we really focus mostly on the GHG emissions. We have used some proxy method, proxy parameters, like the energy input as the main factor. But certainly we will be open to hear from you and from anybody if there's other better published or available methodology to assess GHG emissions. Anybody else from the team who want to add anything on regarding this question? Okay. The next question, I believe, from the same participant: can the experience curve be used to predict the evolution of environmental taxes or other related costs? Maybe Andrew, who looked at the economic part, do you have any suggestion on this?
I would say, from a tax perspective, it would probably be pretty difficult, just because it's hard to. I mean, taxes often they come in the form of maybe like policy and things like that, and it's really difficult to be able to project just how the policy of a certain country or jurisdiction would go. It's an interesting question, and it's very difficult to answer. I'm not sure I have a good response for this, but I haven't seen it in literature before, if that answers the question.
Yeah, I think it's quite, sorry, Andrew, if you put on the spot. Yeah, it's a difficult question. Anybody else want
yeah, I would like to add to this. I think, I mean, especially, I mean, we have the issue, or we face the issue with these learning curves, that it's difficult to do these reliably for environmental assessments, because the processes might be very complex. But we see that there's a lot of use in the capital expenditures. So I assume that if you plan to build multiple plants, and you have related costs that come directly for the capital cost, that you can use these to predict the evolution quite well. But this always will depend on the data availability that you have.
Yeah, I think it's a very good question in the sense that it's all tied on to what's called like we're trying to do, which is science-based decision making. Yes, providing a fair level of playing field between conventional established technology and new emerging technology. It's not that easy, particularly those emerging technology where they need a lot of investment in terms of research now, in terms of deployment. How you can what type of level of taxes you need to have to level that playing field. Yeah, I think it's a good question. I think we don't right now, we don't have any answer.
Sorry, can I add one more point to that?
Sure.
Just kind of considering this a little further, I think experience curves shouldn't necessarily be used to predict things like environmental taxes. I actually would think that it should work the other way, where environmental taxes actually be used based on the evidence that was provided based on these projections. Now, in an ideal scenario, that's what you would want. In reality, it might not be like that, but I think taking evidence for these types of decision-making challenges would be the best way to go about this.
Okay, the next question, I have to admit, I'm not very familiar with, I heard about it, but I'm not very familiar to make a comment regarding using the right law in projecting future cost and environmental impact. I have to be forthcoming on this. Anybody from the team are more familiar with this right law? Okay. Yeah, I think it's the I would love to learn more about this from the person who asked this question. And as I mentioned in the TRL, we are thinking of how we're going to build on the current work. I think as mentioned also by Volker, this is the work has been done the last 2 or 3 months. We will be more than happy to receive feedback and suggestion how to improve or add more or consider past work. And this anonymous attendee, please get in touch with us, and we'd like to learn more about this suggestion about the using right law for the future, for projecting of future cost and emissions. Sorry, I think I couldn't provide any more information on this. The next question, I will read it, please, while my colleagues could think about who can answer this question. Could you please comment on how to choose the numbers of plant as they are directly linked to learning rate? Example, electro reduction, what domain we need to rely on engineering expertise? We cannot rely on petrochemical engineering expert, right? I guess. I guess this is coming from an engineering expert. Anybody from the team? I think it's touched a little bit to TRL and TLC.
I think I can hop in. So first, I'd like to add one point that was mentioned before. So I think regarding learning rates and environmental impacts, it makes sense that if we assume that the overall system is learning, you know, the energy is learning, our yield is improving, that we then apply this onto all the impacts that we have, such as cost and revenue, such as GHG emissions, water use, etc. So it just is fair. It feels fair to actually stretch that out, and we know that this is somewhat of a new field. In terms of method, I think we largely use the methods of Rubin et al. And that CCS community, which we are happy that there's so much work put into this. I'm not sure how this is connected with Wright's law, In terms of the numbers of plant, I think for the mineralization case study, we have chosen a certain market share, right? So if we have 10% of the market share, we know the average size of the plant, then we can say how many plants are required to actually reach that type of maturity for the market. So we assume that if 10% of the technology available in the industry is actually running this type of process, then we can say it has kind of leveled out, or we have that time of maturity. And this is how we have based that learning curve. And I mean, this is subjective, but we have to make one or two of these assumptions. And by actually making these assumptions transparent, we can then help to see how other assessments are working or adapt their assumptions, and thereby having a more transparent and more comparable results. I hope that makes it clear.
Thank you, Arnold. The one thing I want to add regarding the second part of the question, which is what domain, related domain that's from what we can learn regarding the electroreduction or electrochemical reduction. I think the two domain during our literature search, we find some data in the past. It's the two. The first one is water electrolysis to produce hydrogen, and the second one is all the work related to fuel cell, particularly PEM fuel cell, and also solid oxide fuel cell. And also another domain which is a little bit far, but still related, it's the it's battery technologies. Anything to add to this question? Okay. I think we have two more questions. We still have time. I think we still have until 12. If you have more questions, we will be more than happy to help address them. I believe I'm just trying to. Okay. I think team is trying to provide some answers to one of the previous question. Okay, the next question, it's related to the Therl 819 used for Fischer traps. I think it's related to the second case study, but it gains a large variety of hydrocarbon ranging from gaseous to solid ones. Therefore, we need a specific refinery technology for gaining jet fuel only to convert to high molecular weight waxes. So I have some technical doubt about that way to produce jet fuel. I think if you run very well the question, Moni or Ling.
I can take this one. Yeah, I think whoever asked this question, yeah, it is correct that future trope synthesis pathway will provide or will convert a wide range of hydrocarbons, including a small fraction of wax. These are all true. But I want to also mention the other fact that Fischer-Tropsch synthesis pathway has been approved by ASTM as the first alternative jet fuel pathway. It's also called Fischer-Tropsch synthetic paraffinic kerosene. The approval, I think, was done back in 2009, and it is allowed to have the Fischer-Tropsch fuel blended at a 50% blend limit to jet application. So I think it's all applicable. With the wax as a co-product or byproduct, it might lose a little bit of yield, but I'm pretty sure, because we studied some of those hydrocracking technology. If you are able to add those hydrocracking, you can improve the jet fuel yield by cracking those wax. So there are a lot of processing opportunity to improve that, and jet application is all feasible.
Thank you, Ling. Anybody from the panelists want to add anything on this? Maybe one thing I would like to add, I think that this is something has been discussed elsewhere. it's the viability of having standalone CO2 to jet fuel. I think one of the suggestions, probably the most viable approach for this pathway, is to combine, integrate the CO2 to jet fuel integrated with or combined with an existing refinery. I think this is something we didn't consider in the current work, but maybe this is something that could be also assessed, and if time and people are willing to do so. We have 3 more questions. In TLC, it is assumed, okay, I think it's moving. Just trying to read it so that people will take time to think about the answer. In TLC, it is assumed that plant building is happening one at a time. How about parallel building of plants? And what about time needed between building or separate plants to implement learning process kind of data factor? Anybody want to?
Yeah, I can, I think, say something that, I mean, it's correct that so that the learning can occur, you have to assume that these plans are not built at the same time, or at least they have to have a certain time of where learnings can be used. Since usually these data were derived from how different plans costs over time, it's usually derived where you also might have an overlap of a building a plant, and sometimes you don't. So this might still occur. I don't recall that we found in literature someone really taking this apart and saying you can optimize this learning through, for example, waiting always 2 years in between a plant or something like this, so you have all the learnings. But it's definitely an otherwise interesting idea how to optimize this.
Thank you, Dale. Anybody else want to jump into this question? I don't have anything else to add. Then we can move to the next question. It's very, very good. I think we have getting a lot of questions. We have challenges today. Good. Since learning curve are meant to capture learning by doing, are this the most appropriate model to represent the discontinuities that are likely to occur through technology development? I will start. I'm sure my colleagues will jump in on this. I think it's thanks you for asking this question. I think I think this is something maybe we didn't insist during the presentation. It's this separation between learning by searching, where a lot of what's called the discontinuity will occur, and learning by doing. The first one it's the R in the R&D, and the second one is the D in the deployment or development. Certainly, yes. I think it's the learning curve have to capture both, but we didn't dig in terms of details. For example, it was like and including like a possibility of having like this type of discontinuity in the research. This is what is expected in this low TRL, but we didn't specifically include it in our analysis. Anybody else from the team who want to add anything on this?
Yeah, I'll add something as well. We did touch upon it very briefly, but you're right, there are discontinuities. And in fact, there are studies that will look at perhaps the entire innovation process and get one learning rate for learning by doing, or just encompassing all types of learning. And then you'll see other studies that actually look at specific stages. So they'll look specifically at research and look at the learning by researching specifically, versus maybe in the development stage, they'll look at learning by doing and things like that. So I would say that this maybe is like a user choice, depending on how much resolution you have. If you're just trying to model, general processes throughout its entire innovation, then perhaps one learning rate is useful. But if you want more specific learning rates, then of course, looking at these at different points in time might shed more insight.
We have thanks, Andrew, for the clarification. The next question is related to Fischer-Tropsch process. Yes, you're right. It's a good question there. The Fischer-Tropsch has been developed since, have been actually used since before the Second World War. And I think the question is very specific. What specific modification are required to when we combine, for example, electrochemical process to convert CO2 to syngas and combine it with the Fischer-Tropsch process? What are the what's modification or option pathways to improve the overall GHG emissions or the cost of the whole system? Anybody has any suggestion in terms of answers?
I'll take a shot first. So yeah, those two questions, I think they're very similar, especially the boson Fischer-Tropsch on matching a low TRL technology with a high TRL technology. And if you consider those as rate limiting step for reactions, and those slow rate kind of rate limiting step will be the one impact the overall processes most significantly. So the electrochemical conversion or electrochemistry for CO2 conversion will probably impact the learning rate of the entire process most significantly. So that's one thing. Once you put the electrochemistry into the Fischer-Tropsch, there are a lot of things that we need to do on system integration. Meaning the electrochemical conversion is working on making syngas, and then the syngas will go through the the commercial Fischer-Tropsch processes, and the connection between the syngas and formation and syngas utilization is the key part for the process integration. And I do believe there are a lot of things that still need to be researched and fully understood before we actually get into a fully commercialized integrated concept.
Thank you, Ling. I think we can spend a lot of time discussing this point. I think it's something we have. I think the only thing I want to add, it's as you know, there's a lot of electrochemical process has been developed for converting CO2 to syngas. I know one specific technology I'm familiar, which is developed by Curtis Berlinger team in UBC. One of the advantages of the technology is they can really target specific CO to hydrogen ratio that can enable you to optimize the downstream process. But there's a lot of, I think it's in terms of modification, for sure, there's a lot of options there. Anybody else from the team want to add anything on this question? Right, we're getting to the last question. And we are 10 minutes again before the end to 12. What happened to the complexity? Yes, algorithm complexity and TRL estimation, technology learning curve for integrating Fischer-Tropsch into electrochemistry taken as a whole. Oh, maybe I already jumped to this answer already. Yes, anybody from Moni or Ling want to add anything on this?
Okay, I can take this. Thank you for the question. What happened to the complexity and TRL estimation for integrating FT into electrochemistry taken as a whole? Yeah, here comes to, we kind of touched in the methodology section here, like at low TRL technology, at first, like when you estimate technology readiness level of different components of a technology, so the TRL may vary because sometimes a part in this case study, like the electrochemical portion that is integrated with other upstream processes and downstream processes, and the technology readiness level of those parts may be higher. So it creates a problem in a sense, like not all the components of the technology are at same technology readiness level, and also their technology learning curve, technology learning rate will be different because for higher technology, it has more data and more accurate technology learning curve, and maybe lower, but the technology that is at lower TRL may have a higher learning rate. So definitely it creates a complex, and so we can apply the method discussed here, kind of integrated the different technology running rate and come up with the overall learning rate. So that's another approach. And I think Teal also mentioned about the two different methods where you can consider different technology per and the technology learning rate of each component to evaluate, to determine the overall learning rate, or you can just use the overall technology learning rate. Yeah, I think that is that answer your questions. Anybody want to add anything else?
Thank you very much, Moni. I think, okay. I think I want to thank everybody for the question. I want also to thank to all those who attended, particularly those in Europe, which is late now. To close this this webinar, this part of the webinar, I hope we try to address most of the question and the challenges, and I hope also this provided enough info and guidelines in terms of quest to build a scientifically robust TLCA-based decision-making for methodology for these emerging technologies. I will hand up the floor to Tim.
Thank you very much, Farid, and your entire team. That was an excellent presentation on a very difficult, but yet timely and important topic in this field, in beginning to understand how to utilize technology learning curves to improve our understanding of the environmental and economic performance of the CO2 utilization technologies. As Farid and the others have mentioned, this whole process is about soliciting your feedback and getting your input early into this process as we are refining the harmonization of these different methodologies and the approaches. For that you've heard today underneath of both part 1's discussion under the technology readiness levels, as well as under the part 2 for the technology learning curve part. We are excited to continue this webinar series moving forward next week with additional presentations. And so the next one again is May 19th. And so we look forward to, if you have not signed up, please sign up, and we look forward to your participation. If you have additional comments on today's presentations or any of the webinar presentations within this GCI seminar series, we look forward to hearing that. Please feel free to email them to any of the task leads or directly to Volker or I, and we will get them distributed to the appropriate teams. With that, I'll turn it over to Volker for any final last words.
Tim, thank you so much. Thank you everyone who participated today, either as presenter, asking questions, posing challenges. That's exactly what we were hoping for. So thank you everyone again, and have a good evening if you're over in Europe, a very good morning if you're even further east from our viewpoint, or a wonderful rest of the day here in North America. We'll see you next week, and until then, have a good time.